Hi, good morning, everyone. It's lovely to see you all here. Thank you for coming. It's a pleasure for me to introduce Reiko Oda, who's a CNRS researcher. The institute you can see there, the ICB, which is in Bordeaux, which is a kind of a mixed center between the CNRS and the Université de Bordeaux. Reiko did her first degree in Tokyo in physics. Then she did a postdoc in MIT before she moved to France. So she'll tell us about her research on hierarchical chiral objects. So there's a bit of a fashion now, I guess, about chiral nanoscale objects. I would say Reiko was one of the first ones in this area, actually. So she's got a tremendous amount of experience in this area. So if you've got any general questions about the whole field, she's a perfect person to ask. She's got a lot of experience and knowledge in this area. So we're very lucky to have her here. Thank you for coming, Reiko, and we look forward to your talk.
Thank you very much. Thank you, David. And thank you all for giving me this wonderful opportunity to be here and share some of our recent results done in our group. And to visit Barcelona and around. So as you see, I went Montserrat 2 days ago. It was wonderful, and then of course it's like a disease, right? When we are working in this field, everything which turns, I just attracted, and then I saw it, and then I had the Google Translate of what's written on the bottom of this thing, and then it's a beautiful, like stairs of understanding, and apparently, so we are in stones and the flame plants, and then man, and we are going ascend to the knowledge. I don't know what it is, what is the origin of this thing, but I found it was very interesting. So, in our group, we are working on chirality, and as David said, we're mostly interested in the nanostructured chirality, which is usually much bigger in scale than the molecular chirality. So obviously, when we work of the molecular chirality, you have different types of chirality, the axial and propeller and helical. And then you go to polymer, and then you have these helical polymers. You can have the switch inversion, and then you can have the elongation. So all these control on the chirality of these objects. And then you can also have, if you want, the chiral crystals. Well, the tartrate has been the first crystals that we really hear about, but also the quartz. Also, we know that we have a right-hand, left-hand quartz, silica, and so you have these crystals, and then you have the supramolecular chirality, which also has been really there since a long time. In fact, the first reports it dates quite a long time ago, and you see those. So these things starts to be visible. So molecular chirality now with the very sophisticated electron microscope, sometimes you can see, but these are already back then you could see the twisted ribbons, and so it goes from nanometer to tens of nanometers and sometimes almost microns, the helical structures. There are many reports which oops, Seiji Yashima has beautifully reported in this review. And so we are working, starting to work on this kind of thing that you will see. Sorry. So what is really nice about chirality is that chirality is a concept that you see, as you see from very small objects to very large, much smaller than us, to much bigger than us. So this is a known fact. Right hand up. I'm sorry. The chirality. I started the talk with the notion that the chirality is a given fact. So like it's a mirror, you cannot superpose your object with its mirror image. So right hand and left hand is the chiral because you cannot superpose your right hand with the left hand. And all these objects, oops, maybe I should have. All these objects are chiral. It's helical or most of them here helical objects, and they are chiral. because they cannot be superposed to their mirror image. Then the question is, this chiral object that we see through various how to say, size scale and time scale too, but I will mostly talk about the size scale. How do you measure the chirality? Is one object more chiral than the other the other object? Is there a way to talk about it? If we are talking about this spherical object, we can say, okay, this sphere has a larger diameter than this one, so this is bigger than this one. Chiral objects, for example, when you look at these snails, is there all are same chirality? Can you talk about the difference in chirality? Is there a measure? So we all agree that expressed chirality, either in the response of chiroptical properties, can be compared. Like this one has a stronger circular dichirism signal than the other one. Therefore, this one has a stronger response. But is an object, can we define chirality or not? So if you talk to like a molecular chiralist, they would say, no, you cannot say one is more chiral than the other one because object is either chiral or not chiral. And then which, for example, if you compare these things, they are all chiral, but one, is it correct to say one is more chiral than the other one? Of course, if you measure the CD or CPL, circularly polarized luminescence, and then you can say, okay, this object has a stronger circular CPL, therefore, chiroptical signal is stronger, but chirality, no. And, so in our case, we are interested in really a shape, not. So if we are looking at some hierarchical and in the hierarchical and transversal chiral systems, and just we talk about helical structures with different pitch and different same pitch but different diameter, is there a way to then talk about measurable chirality if we only look at the morphology? And of course, if then the continued question will be, if you have the same morphology, but if you change the materials, can you say one materials with this morphology show stronger chirality? Now, again, what are we talking about when we say measuring chirality? So for us, the first question would be, can we look at a helix with the definition of pitch, diameter, and the width when it's helical structure of ribbons, we can also define the ribbon width like this. And then if you stretch, can we see that one is more chiral or the other? In fact, it's not that easy to do this experiment because usually things are very small, so you cannot really control the pitch, like the nanometer scale things. And that's what we are hoping that we give some insight to this question. Okay, so how do we study the effect of these parameters, the pitch and the diameters, and etc.? So purely shape-induced chirality. So we are trying to kind of say morpho-chirality. The name may sound interesting. And then the chiral crystal, and then I will talk later on the chiral crystallization in or on the chiral surface, and then finish with the energetical enrichment using such a chiral surface, nanospace. So the So nanostructures that we have been working on, and I have been working on since a long time ago, you would see from the year of the reference that I started more than 25 years ago on this system, and I keep just talking about this system. But because this system turned out to be very, how do you say it, interesting, and so I just keep working on the system, and I feel like I have shown this slide for millions of times, but I still have to talk about this thing because otherwise I will not be able to show you what we are working on. So this is the surfactant molecule, hydrophilic head groups and hydrophobic tails. And in this case, you have two hydrophilic heads, which are connected by the spacer. So we call it Gemini surfactants because of the two heads. In this case, it is 2 carbons in the spacer. And then here we have 16 carbons. So like 16 to 16. That's how we call it, very simply, 16 to 16. And in the presence of chiral counterions, and then the most promising counterions so far we have worked on is tartrate. Then tartrate is also D-anion. So you have a 1-to-1 mixture of tartrate and this 16 to 16 Gemini surfactant. And what we have shown, so 20 years ago, is that if you have a matching of L-tartrate with the, like you see this molecule itself is not chiral. It doesn't have a chiral center, but you can see this N connection is connected with carbon, 2 carbons, which can be Z conformation or S conformation. So conformationally, it can be chiral, but without tartrate, it's not chiral. It's just going back and forth very quickly. But then, so with L-tartrate, we have shown that it forms right-handed helix, and with D-tartrate, it forms left-handed helix. And these ribbons made with bilayer ribbons, bilayers like this. And it's just this bilayer ribbon is doing this helix, or twisted ribbons. So we could have different morphology of chiral nanostructures. It can be twisted ribbons with Gaussian curvature like this, or helical ribbon with cylindrical curvature. And then if you wait long, it can even go to the tubules like this. Okay. In fact, I knew it a long time ago, but the 16 to 16 was the most easy to work on. So we kept working on 16 to 16. But more recently, with the thesis of Akshaya Kunamal, we are studying the effect of the chain length. So basically, you have a 16. This is what we have studied a lot, but we can do 15 and 14. The only change is the length of the hydrophobic chain. And then what happens is, because this curvature comes from the easiness of this bilayer to curve, which is easier for the shorter chains. So we knew that, but the pitch of the 14 to 14 is smaller than 16 to 16. So it's around 17 nanometer and 50 nanometer in the case of 16 to 15. I don't have the photo, but 15 to 15 shows the helical pitch, which is in between. Now, so this is a chiral structure. When you measure these ribbons in circular dichroism, it forms kind of like an organogel, the fiber-like structure. When you look at it on the CD, what you see is a chiral signal from the tartrate. So in this case, all 3 of them have the same molecule tartrate. However, if you measure the CD of 14, 15, 16, they have different magnitude. So 16 is around 3 to 10 to minus 3, whereas with the 14, it's 5 times higher. Although it's the same concentration, of course, it divides by the concentration. So, but it's just that how this tartrate is organized supramolecularly simply modifies the amplitude of the G factor when you compare 16 to 14. So that's already nice, which means pitch, smaller pitch leads to higher circular diapason signal. So that, keep in mind, now also quite a long time ago, in collaboration with a Japanese group, we first developed how this organic self-assembled molecular systems can be stabilized. So we did different things, polymerization, and what worked very well since then was the silica sol gel transcription. So what you do is you just come with the prehydrolyzed tetraethoxysilane, which is negative, so they are attracted to the surface of this cationic surfactant self-assembly, oops, like this, and then they polymerize on the surface. So you go from self-assembled organic molecule to silica, purely silica walls, because once you have the condensation, then you can remove the organic molecules. So in the end, you only have here SiO2 thin wall, which makes this helix. So on this photo, so this is the organic, and this is inorganic. It keeps the morphology, and then you have really thin, like 3 nanometers thin silica wall on both sides of the organic helix. Oops, like this. So you see, yeah. And so you have, again, you have a left-hand helix from the D tartrate and right-hand helix from right-hand from the L tartrate. It's always confusing. So, and then we managed to find a way to have them in a individualized suspension, which is not very easy from starting from organic gel because they are entangled and everything. So we optimize the way so that we can have this individualized silica helices of around 500 to 1 nanometer to 1 micron. So now we have a very clean silica helices. It looks like this. I don't know how we. I don't think. Tries. Oh yeah, here, yeah. Oh, the other mouse. Okay, and there are many mouse. Okay, oops. So this is a tomographic image done with Ovidiu Hersen from Strasbourg. So this is the silica helices, like you see. This is left-handed, and then if you cut it, like if you cut it perpendicular to this thing, you see like a croissant shape. It's better, yeah. You see like a croissant shape thing which is turning as you go up on the axis, and then you see that inside is empty. This empty space was where the organic molecules used to be, but when you wash it out or you calcine, and there's nothing inside, so you have an empty chiral croissant type shape which is helically going through the axis. And then if you cut it parallel to the axis, and then you see again, you have the empty nanospace here. Now, I just want to spend some time on this silica helices. Silica itself may not be an interesting object as it is. It's not conductive, it's not emissive or anything. It's a transparent thing. But we wanted to know, so it's an amorphous silica. It's not crystalline, it just has a shape. But as you see, it has a VCD signal, vibrational CD signal in an infrared regime, not in the UVs because it doesn't absorb, it doesn't emit. But so it's an interesting object, very fundamental question, but I'd like to share with you on this object, why they are chiral and how they are chiral. So this is really the work of Yutaka Okazaki, who is now in Kyoto University, and with the collaboration with Thierry Buffetot, who is my favorite collaborator from Bordeaux University, who's a specialist in vibrational spectroscopy. And so VCD, we did the VCD. So what we have done is, so you have, you know, this Gemini length, spacer length. So 12 to 12 is too short, so they don't form helices, they form only micelles. But you can always have the tartrate with this Gemini. And then 16 to 16, these ones we know that they form either twisted or helical or tubules. And then so we wanted to make sure that the VCD signal that we see from silica does not come from the molecular imprinting of tartrate. So 12 to 12 tartrate still has the tartrate, but if you create the silica transcription of silica particles from the organic molecules, you have no VCD. But when you start with 16 to 16, then you have a very nice VCD signal, which is the highest for this morphology. And then when it goes to the tube, it's interesting because it's a tube. So morphologically, it's not chiral. And then the signal goes down. You still have some VCD signal. And then we think it's because of the memory effect of the original shape. And I'm sorry, one more thing which is interesting is because it's silica, you can calcine them. When you calcine, what happens is SiO-Si connection everywhere. And this OH, there are many OH which has not reacted, so they're pointing out. And this OH, when you calcine, they form the SiO-Si bond. So you remove the OH as you go up. Around 600, you have no OH anymore. And at the same time as calcination, what's happening is that you shrink the whole dimension. So the diameter, the pitch, and in the width of the ribbons, everything goes down as you go. You heat up from room temperature to 1,000 degrees, which means like this. So you go, you shrink and shrink and shrink. At some point, the two walls merge. And then if you go beyond 1,000, you just lose all the morphological, helical morphology, and then you just become the nothing chiral. And then the VCD increases as you go down in the pitch. And then when you lose the morphology, no VCD. So it really comes from the morphology. The VCD signal comes from the morphology. And not only that, as the pitch goes down, the VCD signals goes up. So again, this is, I think I would not go, so this is a study which we were really asking ourselves why this VCD signal, what is the origin of this VCD signal? So in the end, just to say the conclusion, we think it comes from these rings, SiO-Si rings. So in the silica, there are many of these SiO-Si rings. And then these rings, when you shrink, when you minimize the energy, they twist. And except when you have a symmetrical chair or boat shape, when you are twisting, they are chiral. And then you can do the simulation and show that these chiral systems show a very nice VCD signal. So basically, by shrinking, you're twisting more, and then they might be the origin of the chiral signals. So this is from the calcination and shrinking and increasing the VCD signal. This is what I showed before in the organic helices. Again, shrinking depending on the length of the chain length, and then again the CD signal. So this is a UV VCD signal, and this is a VCD G factor, and both of them goes up with the pitch. So we would like to know if we can show this as a general observation or not. Really morphologically induced chirality, do they really follow the pitch? It's not probably the pitch, it's pitch divided by the diameter, but we don't know. So now we have this very nice, but not alone, very interesting silica platform, helical platform. So it's like a helical stairs. The stairs itself is not interesting, but it's because we can climb up or we can put things on top, and that's when it becomes interesting. Now, when you compare with the molecules or particles, these helices are much bigger. So then let's talk about how the chirality is transmitted from one object to the other one. Usually we talk about the enantiospecific recognitions, the molecule to molecules, and then it's very important, the chirality of one, so that the other one can recognize or not the other one, not the other molecule. Usually we talk about the object with similar size. So what happens in our case, our helices are huge, much bigger than the molecules. If you look at it like this, does this man care what if this big hand is right or left? So when you have a mismatch in the size, does it affect the chirality transmission mechanism or not? Or can we still get around it and use this big, huge platform for the recognition, the induction, and the enrichment? So this is what we are really interested in. So the first thing is chiral induction. We have this big helix. This is typically what I draw, the circle is the typical molecular size compared to our helices. So it's really small compared to the helix. Does this guy know what if this one is right hand or left hand? So that's the question about big helix with small objects. And yeah, so yes, can we still induce the chirality so that the other one becomes chiral? To do so, we have been working on various molecules and nanoparticles in interaction with our platform. So transparent, not in itself interesting in itself, but interesting shape. Does this guy do things to the dyes and particles? Of course, the answer is yes, otherwise I wouldn't be talking about it. So here there are some examples of nanoparticles, metal complex. Anything basically you can complex on this helical stairs. Original particles or complex are not chiral. So here it's a gold nanoparticles. Nanoparticles before grafting is not chiral, but when you graft, you induce very nice circular dichirism signals just because they are organized. So supra nanoparticle organization. So right hand and left hand, of course, induce opposite signal of CD. The right P gold helix and M gold helix. More recently we did the similar thing on this COSAN, the cobalt complex, and then this guy, when they are complex, they have opposite signal. Not only that, this one has shown the nice capacity on doing the enantioselective photocatalysis. And then also we could also organize the perovskite. So these are more CD, but here you could also induce the CP, circular polarized luminescence, from achiral crystals organized around the chiral stairs. And not only the particles, so sorry, yes, so all the PhD students who worked on this signal, on these systems are shown, so Pei Zhao and Jie and Hao. And also molecules, basically any types of achiral molecules, just we put them and then they show induced CD signals. In this case, they are mostly anionic molecules because in this case, we made them cationic and then made them complex. But more recent study that we are running, you don't need to be anion. We can just basically increase the interaction between the molecules and the silica helices, and then just they organize around and then they show induced CDs. And so this is in the case of TPPS, and you have thread band and Q band. Both of them have very nice induced CD signals. So this was about the induction. Remember, the inside was empty. So when something is empty, we would like to fill it with something. So that's what we do here. Can we use this nanospace for something? And so here we have the organic molecule, the original Gemini surfactant. You have hybrid coated with silica. So now organic and inorganic hybrid nanohelices. Here, this is interesting because pink, what I showed, pink is the 16 to 16, remember, the Gemini surfactant. The blue is the tartrate. So you have the 1-to-1 complex of Gemini tartrate, forming these bilayers. And once you sort of stabilize with silica walls like this, then you can use it like an ion exchange column. You come with something, the salt solution, and you can exchange this tartrate by the gold salt in this case. So you have now gold salt which are organized instead of tartrate here. And then you can see the induced CD from gold salt in the UV regime, which is quite interesting. But then you can do the in situ reduction from gold ion to gold. That's what you see here. So now you see the black dots are the gold particles after the reduction from ion to metals. And then you could see, you could see that here you see that it's really the gold particles which are inside silica. This is different from what I showed before where the gold nanoparticles are organized. In that case, we need to have the gold nanoparticles which are very close by to see the overlapping of the electromagnetic field to see the induced CD. In this case, they are not very close. They are individually dispersed inside. You can see they are inside the silica. And then you could still see the CD signals from these gold nanoparticles. And then here we denature the silica by a very basic solution. So now silica lost their morphology, but still you keep the same CD signal. So it's really individual gold nanoparticles are chiral in this case. And what we did was then we did the tomography of this individual gold nanoparticles. And then we used this surface shape to simulate what the CD signal should be. And then the right-hand helix, it matches the sign matches. It's much sharper here because in this case you have a big and small and different shape averaged in this case, but here it's from one particle. You can change the reducing agent, and now instead of forming nanoparticles, isolated nanoparticles, but you can have the helical gold. So now you have a ribbon here, which just grew inside the helix. So you had the ions, then they become gold, and then when they grow inside, they cannot go anywhere. They have to follow the helical nanospace. Therefore, they have to grow like this. And once you have this helical gold, then you can even remove the silica, and then the gold ribbons remain stable. So you have the helical gold created by the nanospace. And so yeah, sorry, I forgot to talk about. So this is a collaboration with, again, the same Yutaka Okazaki, who is in Kyoto, and also with Professor Fukami, who is in Kyoto University. So it's a collaboration with their group and our group, and with people, and then Wijaku Spania and Zakaria, who have been working on this system. Well, Zakaria left, but anyway, okay. And so again, here again, the tomography, you see that this is the gold ribbons doing the helix. And in this case, the plasmon signals goes all the way to the infrared regime, and quite strong signal, 0.2 G factor. And then, so this part comes from the length. The gold particles typically have the plasmon signal in the 500, 600. But, and then when you increase in one direction, then you could have this very red shifted signal. And then this position of the signal depends on the length of the helix. And then, so these are crystalline. And then you could look at along the ribbons. In fact, the crystalline facet is rotating as they grow. And yeah, so it's about the gold helix. Now, we could similarly use this method to do the perovskite. In this case, the method was a bit different. So, and this starts to become a method which is very easy. I don't know if you say easy, but it's a very versatile method that I'm going to talk about. So basically, you have this gel, right? The silica gel with this ribbon. And then you drop cast on the quartz surface. It looks like this. It has to have certain amount. So between 50 or 100 microgram per centimeter square, you drop cast to have a homogeneous surface, which looks like this. And then you come with, in this case, you come with the solution of these ions. And then do the same thing. You drop cast on the surface and then let it dry. And then what happens is they form these crystals inside this silica. And so this is a work with of Peizo Liu, with again Yutaka and Takashi Sagawa. And so you can see that the crystals form inside the clear gray thing is the silica, and then they crystallize inside the silica in the nanospace. The helical perovskites, which are crystalline and which shows very nice CD and CPL. Again, this is purely because there is no ligands here. There's nothing organic molecule here, so it's just simply because they are helical that they show. Oops. They show CD and CPL signals, which were confirmed also with the simulation done by Yambati. Oops. So you can crystallize inside, but more recent thing we haven't done, so it's a really recent work. We can also crystallize on the surface. So this is with the work, with the tetraphenylethylene. So this molecule, in fact, are known to do the aggregation-induced emission. And also they are propeller-like. It looks very flat like this, but in fact, they can have a M-type and P-type conformation. And then there had been studies on these crystals, the right-hand and left-hand crystals. And so this has been already reported. And so this is a PhD thesis of Anthony Boudier in collaboration with Dario Bassani and Guillaume Raffi. And so what we wanted to do is what happens if you do the same thing, the drop cast of silica helices, and you come with a drop cast of the solution of TPE, what happens? And then again, we saw very nice CD signals, right hand or left hand, positive or negative. And sorry, and it's not the silica scatters. So that's another question I'm not talking about. So we have to be careful about the chiral scattering coming from silica. But in this case, we also do the DLCD, so using the integration sphere to get rid of the chiral scattering. So anyway, so they form CD. They also show CPL emission. So the question is it the same thing as what we saw? But with quite a bit of dispersion, the signals is not as nice as CD. So we were wondering why the CD is quite defined and CPL is not well defined. Still, it is handedness dependent signal. And then when we looked at it, in fact, they do not form inside, but they simply form on the surface. So this is a very low magnification of an optical microscope. When you go up a little bit, it looks like this, the crystalline crystals, which are formed on top. So you have the silica surface, silica helix surface, and on top of it, they are much, 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 much bigger than the silica helices. So they are just sitting on top. And then, so this is a hyperpolarimetric image done by Guillaume Raffi. This one just shows that they are, what is the linear dichroism of these crystals. Basically, if you have one color, it is a monocrystals of this one. So which crystal, is it right or left? We don't know. And then when you cool down very quickly, they form very different types of, again, on the surface crystallization. And it seems like we have less correlation between the handedness of the silica with respect to the CPS signal, at least on the CPS signal. So what we think is happening in this case is that if we crystallize, they do not go in, so they can coat the surface of the silica. So CD comes from the coating of the silica, but also the crystal on the surface. CPL only comes from the crystals, the crystals which are formed on the surface, because these TPE does not emit, only crystallized TPE emits, and they are the origin of the CPL. CD is coming from everybody. So what we think is maybe it's a seeding type of crystallization, and it seems like we are able to induce the chiral crystallization of TPE in one of the propeller and not the other one. But it's not perfect. We have to optimize, so there's a mixture of M and P type crystals on the surface. But we are hoping that with the optimization of the conditions, maybe we can use this surface as a chiral crystallizer simply on the surface. Yeah, this would be the dream of this. Okay, now I would like to finish with the enantiomer enrichment story. So we would start with the story between our helices and the foldamer. The foldamer is like the helical molecules with the very well-defined helical structures in this case. The foldamer that we will be using is, again, very, very small compared to our helices. So the question was, is there any interaction between these small helices and our big silica? So this is a collaboration with the group of Jan Ferran in ICB and the study of Pianam Prani and Robin Hess, PhD students. So they had been working on this the foldamer, which are designed to form helices. Without any chiral inducer, they can form right hand or left hand, a half and half. It's a racemic, but they have to form helices. So racemic mixture like this. So this foldamer has been developed by Ivan Huck a long time ago, and then so Jan is developing this aspect of this foldamer. Now, they had already shown that if you have a chiral inducer at the edge, not the edge, the end of this foldamer, then you can completely shift the handedness, control the handedness of this foldamer. So this was molecularly controlled P or M handedness of the foldamer, right? Now, so we have the racemic foldamer. We call it Q4 because it's a 4 mass. And then when you put them together, and then in the presence of camphor on the right, on the R or S, and then you can control left-hand helix or right-hand helix. This is only foldamer, and then they have shown that there's a CD and CPL. Now, let's see what happens between this guy and our helices. So we did the same thing, the drop cast, very simple thing, drop cast of the silica helix, and you come with M or P helix. And so this is what you see. So right hand, left hand, and right hand foldamer with left hand helix and right hand helix. So you have 4 configurations like this. And then when you measure the CD and CPL, you see that P and P, so right and right, or left and left, shows the exalted signals. So molecule alone is smaller than here. And then when you have a matching handedness, and then you have a exalted CD signal, which is much more obvious in the CPL signal. So this is the matching, this is the mismatching case. Mismatching one, the molecular CPL is almost erased by the helical CPL. So this is what we would call hierarchical systems, the chiral systems. So you have a supramolecular chirality and a molecular chirality, and then you have a matching and mismatching system in this case. Now, this is about the chiral molecule and chiral silica helices. Oops, sorry. Yeah, and the matching and mismatching here, matching. Oops. Now, let's remove this camphor and go back to the racemic helical foldamers. And then you drop cast this racemic thing on the silica helices. And again, you have induced CD and you induce CPL. Without silica, the black thing would be the racemic foldamer just drop cast on the substrate. Of course, you don't have any CD on CPL, but if you put them on the silica, you have an induced CD and CPL. Now, why do you see this induced CD and CPL? You can think of 2 things. They stay racemic, but supramolecularly they are organized in the chiral space. Therefore, you could have the racemic but supramolecular system. Maybe more interestingly, being in the chiral nanospace, we could induce some enantiomer enrichment. One of them switched to the red switch to black, not the black, it's blue, because they are more happy in the nanospace. So the question is, which one is it? What we are seeing? It's very difficult because they are inside, so you cannot separate the molecular and supramolecular aspects. So Pianan did a really hard work. She tried to wash it out from the silica and separate the molecule inside and silica, and then measure the solution of this molecule and then do the CD. The problem is, as soon as you remove silica, they go to they racemize. So you have to measure it very quickly. She did lots of experiments, and then this is the average of the signal. But you clearly see the effect of the original silica handedness, which means it was so. And then so when you wash, you remove and then you wash and then you put in the CD and then click. The fastest you can go is 3 minutes, and then 7 minutes it racemizes completely. So it was a really hard work for her to do that. But after many things, so she could see that it is the, and then from that you could extrapolate what should be the enantiomer enrichment inside the silica at 0 minute, and by comparing with the chiral foldamers, we know that it's not so much. Enantiomer enrichment is something like 4%. So very little minority comes from the deracemization and enantiomer enrichment of the molecular CD. And in this case, the majority comes from the supramolecular organization of these racemic foldamer. It's still very weak, so we need to optimize it. So very recently, what we are doing is it's better that your system does not racemize. So we are using another system in collaboration with Sawada from Institute Technology of Tokyo, but they changed the name, Institute of Science Tokyo. They changed the name of the university. So what they have is this gold, not the gold, the silver ion complex with these peptide ligands. And then they have shown, it's already known that they have a double helical ring. So they have already shown this. And then you can, so of course they are either this way or this way. So you can have an M-type or P-type helix ring. So this was not known. So what we have done is it possible to do, and so if you could, if we do this formation of the rings inside the nanohelix, can we see? And then once they are formed, then they don't racemize. So then it's easier. You don't have to do everything in 3 minutes. So that's what we are trying to do. And then indeed, So if you have this the ring with thin film of silica, you have a positive and negative signal depending on the silica handedness. But if you remove, first, you don't have any CD. However, if you do, the annealing of them, annealing, once you are there in the silica and then they can move around inside the silica, now you see clearly, and then you wash out and then you measure outside in solution, you do see now a very nice CD signal, which is, this, I should have shown in G factor. So this one and this one is relatively close in G factor. Because this is 0.3 and then 0.1. Anyway, so which means just by complexing inside the nano-chiral space, they formed 100 ring, preferably with respect to the other one. So this is really a chiral space-induced chiral formation of chiral rings. So I finish here. Right now, our dream is, can we use this purely morphologically chiral silica helices, of course, for the separation, just pack them in the column without any chiral molecules. It's just purely shape, morphologically chiral. And then can we use it as a separation? That's one question. And it can be either even more interesting if you could come in with a dynamic chiral system, and then by the time it goes out from the column, can we enrich one of them? And to do that, again, we come out with racemizers. So there has to be a way to somehow freeze the chirality at the bottom of the column. So that's what we are trying to work on right now. So I hope I could convince you that very, very simple molecule, you saw this original molecule is very simple, tartrate is really simple, but from that we went to silica with a very cute shape. Silica itself, again, is not very surprising, but by doing it, the nanospace, you could go to the gold or you could go to the perovskite and you maybe form the chiral crystals. Right now we are working also with carbon, so using this platform to form graphene type carbon helices. And to do the chiral induction crystallization, I didn't talk about the recognition, but it seems like it is working also with the recognition, and then enrichment, separation, and enhancement. To study various phenomena, catalysis or magnetic thing. This is mainly done with Emily Pouget in a group, and also we are trying to do this cis effect thing, and etc. And these are really collaboration with many different people from from different expertise and from different continents. So from our group, but also from Bordeaux, from France, and from Italy, and from Japan, and the students and postdocs who worked in this system, and the funding agencies. And I thank you for your attention.
Thanks so much, Reiko, for the beautiful talk. Are there any questions for Reiko?
Yeah. Thank you for the nice talk.
Thank you.
I know that you said that working with the 16 change molecules were simpler than with the others, shorter. But what do you expect for that cases in the enantiomeric separation and so on? Because the pitch is smaller, the curves are
Yes, yes. So, well, there was no proof that the shorter one is better, but right now we do, because with the VCD and LCD, so smaller one seems to have a higher signal. We always wanted to go to the smaller one, but the 14 to 14 is very soluble in the room temperature. So you had to do everything at 4 degrees. So Akshaya did a lot of work, and now we have the silica with the 14. So right now we would like to do basically everything we did with 14 and see if the induction and everything can be even better with 14. So that's the objective. Yeah. Thank you.
Any other questions?
Thank you for your talk. So I have a question. Is it possible to use these silica helixes as a starting point to grow from them, like metal organic frameworks or covalent organic frameworks? Because I'm working with them and I'm interested, like, is it possible to use them as the starting point to grow the chiral nanoparticles, others?
Yeah. So you put some kind of seed and then on the surface, and then can you control the growth in one sense? I think so. We haven't done this. It might be very interesting yeah. There were people who are trying to grow, her name is Miki Hasegawa from Tokyo. She is sort of trying to grow the stack of porphyrin. I'm not quite sure what, but anyway, she's trying to grow something from the surface. I don't think it's working very well for the moment, but so I'm pretty sure we can grow like the crystal formation of TPE. I think it's possible to functionalize the surface and then grow things on the surface. Yes, yes.
Okay, thank you. Also, you have very nice earrings as the helixes.
Thank you. I bought it in Barcelona yesterday. Yes, thank you.
Thank you. My question is probably very naive, but I'm curious to know why the surfactant that you were showing at the beginning that forms by layers, why these bilayers start to form things that are helicoidal in shape?
Okay. So these Gemini surfactant, in fact, they want to form just flat bilayers because the area occupied by the head groups and the tails are similar. So that in the packing parameter, like is ICBD thing, so they would like to form bilayers. But then it's a crystalline structure, so you have a bilayer, and then you have the tartrate, which is very closely positioned. And then the tartrates form a hydrogen bond, and then we have a crystal structure with an X-ray powder diffraction and everything. So there is a very nice network of tartrate on the surface. So you have the Gemini, and then tartrate is doing this, and then tartrate between them have a hydrogen bonds, which is twisted with respect to the organization of the molecules. And that's why you have a sort of stretching on one direction and not the other direction. Yes.
Thank you.
Thanks.
So much. Any other questions?
That was
Any other questions? No? I have one, if I may, Reiko.
Yeah.
I mean, you showed a lot of growth of materials on the silica helices.
Yeah.
Do you always use the same functionalization on the silica helices, or does it depend on the material that you're depositing on top?
So in fact, we have different, either we go with the hybrid, so the cationic surfactant silica, and then use this cationic surfactant as how do you say, as a point to attract the anions. So that's one way, it's a hybrid method. That's how gold is done. Or you can do the silica, and the surface of silica, we do it with the APTS, which is so then you functionalize with amine. So theos, APTS, and then you have a silica, which is normally anionic, becomes cationic, is amine. Then you can do the amide coupling with the anionic thing. So those are mainly the ones we do, but sometimes we do like a hydrophobic functionalization on the surface so that they can move around more easily. So yeah, it's mainly based on the silica chemistry. Yeah.
I mean, the reason I was really curious was for the TPE work.
Yeah.
So, I mean, that's obviously very hydrophobic. So was that done with a hydrophobic?
Yes. So in this case, I don't know, maybe that's why the TPE doesn't go on, but in this case, the TPE is in the organic solvent, and then you just force them to crystallize. So the optimization, indeed, what we are trying to do is if we functionalize the surface with something which allows the stronger affinity with the TPE, and maybe the crystallization is more efficient, yeah. Yeah.
Thanks very much. Last chance for questions. If not, let's thank Reiko again for the wonderful talk, and thank you for coming. Thank you.
Thank you.